In echocardiography, mitral valve area can be estimated by several methods. Most commonly, we use the planimetry. Cross-section can be planimetered in short axis view. That is the first method usually employed. Then this pressure half time is the next commonly employed using Doppler echocardiography. Sometimes proximal isovelocity surface area, that is this surface area here, can be calculated by PISA method, and mitral valve area can be calculated. That is a cumbersome method. So most commonly used are mitral valve area planimetry and mitral valve area by pressure half time. This is simple and can be measured even if we are not getting a good cross section by 2D echo. This is measured in the apical 4-chamber view. You align the cursor along the good mitral jet and get a good Doppler tracing like this. And all you have to do is mark the slope, that is from the peak of the E wave. This is the mitral E wave and this is the atrial systolic A wave. Just mark the slope and machine will calculate it. You know that in mitral stenosis, when the gradient is continuous, there is no diastasis, and these two waves are rather fusing here. Without mitral stenosis, these two E and A waves will be independent waves with a nearly horizontal baseline in between. That is not there in mitral stenosis. Because of stenosis, there is continuous gradient between left atrium and left ventricle. That's what you are seeing here. So here the measured pressure half time is 163 milliseconds, and the corresponding mitral valve area calculated by the machine is 1.3 square centimeter. Pressure half time of 220 milliseconds will correspond to 1 square centimeter of mitral valve area. If you divide 220 by the observed pressure half time, you get the mitral valve area. And we know that pressure is equal to 4V squared by Bernoulli or modified Bernoulli equation. So the corresponding velocity will be related to the square root of the peak pressure. This is measurement of mean gradient by tracing the envelope of mitral pressure pattern, that is the mitral inflow Doppler. Here you can see that maximum velocity is 2.56, mean velocity 1.7, and peak pressure gradient is 26.3. That's significant mitral stenosis. Mitral valve area calculated by PHT has its own limitations, especially in the immediate post-balloon valvotomy situation where there is an abrupt hemodynamic change. Error increases if there is significant mitral regurgitation. How was the pressure half-time formula derived? The value 220 in the pressure half-time formula shown above is an empirical constant derived by Hartley and colleagues. The relation between mitral valve area and fall in left atrial pressure when the mitral valve opens was noted as early as 1957 by Morrow AG and associates during cardiac catheterization studies. Leibniz et al. Later used the pressure half-time derived by cardiac catheterization to estimate mitral valve area. In 1979, Hartley J. and colleagues described the Doppler assessment of pressure half-time. They later derived the empirical formula mentioned above. Thomas J.D. and associates gave a method of derivation of the pressure half-time formula using a highly simplified model of the left atrium as a box with a side hole in which water was filled to a height and released by opening the orifice. They showed by a complex mathematical calculation that pressure half-time should vary inversely with mitral valve area. Their model also suggested that pressure half-time would vary proportionately to net left atrial and left ventricular compliance and to the square root of peak transmitral gradient. But this complex relation was masked in clinical situation as pressure and compliance would vary in opposite directions. They noted that in settings like balloon mitral valvotomy, left ventricular hypertrophy, and aortic regurgitation, this relation between pressure half-time and valve area would be altered. This explained why our study also showed that pressure half-time method was not very reliable in the post-balloon mitral valvotomy period, where the changes in initial pressure and compliance may be large.